Okay, let's look at how our circuits react at different frequencies. Using a value of 10 microfarad for the capacitor, let's present the high pass filter with a 1 kilohertz signal. Now at 1 kilohertz, this capacitor has total resistance or reactive capacitive reactance or resistance of 15.9 ohms. Okay, so we have a 15.9 ohm resistor here, we have a 1.59 ohm resistor here. Most of the voltage is going to be dropped across the capacitor, so we have 1/10 of the voltage out, 1/11 of the voltage out that we present in. Okay, because there's 10 times resistance here as opposed to the resistance here. If the signal is 10 kilohertz, then this capacitor acts like a 1.59 ohm resistor. Sound familiar? We have an equal voltage divider, 1.59 with 1.59, we'll get exactly half V out of what V in is. So if it was a 10 volt peak to peak, we'll get 5 volts peak to peak out. So it's a simple voltage divider circuit, equal values. At 100 kilohertz, this is 0.159, okay, 10 times less than this. So we'll get the majority of voltage dropped across this. So we'll have 1/10 voltage across here, and 9/10 across here, or 11s across here. So V out will practically equal V in. So as you can see, the higher we go in frequency, the more V out we're getting. Okay, so high pass filter, high frequency passing, low frequency practically blocking. Now, looking at this circuit, okay, same calculations. At 1 kilohertz, this resistor becomes a 15.9 ohm resistor. This one is a 1.59, so we're going to get majority of voltage dropped across this. Okay, so at low frequencies, 1 kilohertz, most voltage is going to pass straight through. 1/11 is going to be dropped across here, and the rest is across there. So V in, V out equals V in at low frequency. 10 kilohertz, okay, equal voltage divider. V out will be half V in, okay. 1 kilohertz, this equals 0.159 ohm resistor, okay. So short circuit, so we're going to get all of the voltage dropped across this, and a short circuit here to 0 volts due to the frequency of 100 kilohertz. So this is a low frequency pass, or a low pass filter. Okay, let's look at capacitors with respect to power supply noise filtering. When we have a circuit that requires a 12 volt DC positive supply rail, we want that rail to be constant with no what we call ripple or noise impressed upon that rail. The ripple noise will affect our electronics, it'll cause things to switch when they shouldn't switch, etc. We want a nice stable positive supply, okay, with no noise on it. So imagine that we're operating in an area, our equipment is sitting in an area where maybe there's transmitters, whether they be TV or radio transmitters like the old CB radio operating on 27 megahertz. This used to happen quite often, it'd be affecting all sorts of things. We would get a 27 megahertz, right, 27 million times a second signal impressed upon our power supply rail. Okay, so we have 27 million cycles a second, okay, would sit on here as hum or noise. Okay. Now these varying levels affect our electronics, they play havoc with it. So what we need to do is we need to come up with a way to get rid of that, okay, or to filter it. So if we took this capacitor, place this capacitor in, and we made it a 1000 microfarad capacitor. Okay, 1000 microfarad capacitor. And we put it into our formula, XC equals 1 over 2 pi FC, where F is 27 megahertz or 27 million. 1000 microfarad, we would come up with 0.0000589 ohms or XC. Okay, so this here would act as a short circuit to that 27 megahertz, shorting it directly out to 0 volts. Okay, gone. Very, very short circuit. You know, I don't think you can get much shorter. And that's how we filter power supply noise. Okay, children, you should have left the room by now. If you haven't, please go. Come on, I can hear. Go, go, go. Close that door behind you. Yes, good, okay. Now, two nuns are sitting in a bath, having a bath. And one nun turns to the other and says, "Where's the soap?" And the other nun turns back and says, "It does, doesn't it?"